Okay, last time we looked at transportation models and the method for solving them. Now we're going to this is going to be a short lesson looking at some non-traditional transportation models. The idea is that although we have this transportation model that's classically set up as shipping goods from one set of warehouses to a set of demand points, it's there are problems that are a little bit more general than that that can be described in the same way and can use the same method for solving them because it's a very efficient method for solving these problems. So we're going to look at just a couple of examples for here. Here's an example. A tractor company must supply the following number of tractors, but they can only produce a certain amount during regular time. So during regular time, they can produce 18 tractors a month. If they go into overtime, they can produce 5 more per month. During regular time, it costs $4,000 to manufacture a tractor and $6,000 during regular times. But there's also a penalty. So holding a tractor in inventory has a certain cost. So this is a question about how can you schedule production when you have different costs at different times for your production. On the surface, it doesn't seem much like a transportation problem, but if you think about it, what we have here is a bunch of ways of supplying something, and we have a certain demand. So our demand is given by those numbers there. So for January, we need to produce a certain number of tractors. Now the question is it better to produce things in January in overtime or carry things or to produce them in February in a different way? If overtime is needed for some of it, how is that calculated in and what's the best way of doing it when there's a penalty for carrying things over? So let's look at the problem. This is the problem made up now as a transportation problem. So we have our demand. We have 3 months. We have a demand of 20, 15, and 19 in each month. But what about our supply? Our supply, we have 6 components to our supply. And in each of those, we know we can produce 18 at regular time, and we can produce 5 in overtime. So we have a certain supply, and we have a certain demand. Notice that these aren't balanced. You add those up, you get 15 more than your demand, so you can supply extras. So that means we have to have our extra column in here of some unmade, right? It's called unmade, but it really is just about it is about having the dummy column for capturing the excess supply. Now let's look at the costs that are in here. This is pulling together a couple of the ideas from the last thing, looking at, we talked about shipment lines that were impossible last time and using a big M for that. Well, look at what we have here. If you're producing something in February, you can't deliver it in January, obviously, because it hasn't been made yet. So we use the big M to say we can't satisfy that supply line. It's an infinite cost. We can't do it. And the same thing for the next month. Anything you produce in March, you can't deliver in February. Now, what about the costs? Well, shipping a unit that's made in January costs $4,000. But if you make it in January and ship it in February, we said that there's a penalty of $500. So that's built in here. Shipping in January, or building in January and shipping in February has an extra $500, so it's $4,500 for the cost for that. And then it's $5,000 if you make something in January and deliver it in March. So we've made these discrete items where you can make it in one and deliver it in another month. Now we have a classic, or we have set this up as a transportation problem, and we can use our transportation algorithm on it. So feel free to go ahead and try to solve this problem. You'll see that the first thing that you're going to do is the first step says to choose the smallest shipment. Well, the smallest number for your shipment, well, you have a whole bunch of zeros here, so you can take your pick. You can pick anything in that zero column and start from there. So we start from there, we would have shipping 5 through there, and we would rub out that line, and you continue from there. Here's another example of something that is not a traditional looking shipment problem, but can be formulated as a shipment problem. So we have a garment company providing caps and gowns of 4 graduations, 1 per day on Monday through Thursday, and we have our requirements. So we have a certain number of things that have to be delivered, but now what about production? Can we take that production and break it up into these discrete groups that kind of act like our warehouses? Sure we can. So here it says that there's 600 on hand, so they have 600 things sitting there. They can purchase new sets, or they can wash used sets with either a 1-day service or a 2-day service. So we've got 3 different ways of supplying the demand. We can purchase a new set, we can wash a set that was used the day before, or we can wash a set that was used 2 days before. And the question is, how many sets can be bought new and how many washed using each service in order to minimize costs? So if we just think about this problem, we have 600 on hand, so that means that we need we need more than that. But starting on Monday morning, when the first piece has to be delivered, we already have 600 on hand, but we need 200 more. So how can we satisfy that? Well, for Monday morning, there's only one way to do it. It's by buying new. But what about Tuesday? Tuesday, there's a demand for 600. Do we buy more? Do we clean things from the day before? We can set this up as a problem in this way. So we have 4 sets. If you remember, we have demand on Monday, Tuesday, Wednesday, and Thursday for a certain amount. Notice that on Monday, it said that we needed 800 on Monday, but we have 600 already on hand. So our demand on Monday is actually only for 200 more. So our demand on Monday is for 200. Then we get into questions about whether or not we should buy or clean. Well, purchasing something new for Monday, Tuesday, Wednesday, and Thursday is the same price for all of them. If something is used Monday, we have a couple of choices with it. We can clean it for 1 day or we can clean it for 2 days. So if it's clean for 1 day, it's on Tuesday. If it's a 2-day cleaning, those can either be used on Wednesday or Thursday. So the cost of cleaning something Monday, using it on Thursday, is still $2. And we have the big M. We can't wash anything and have it ready for Monday because we don't have anything that's unused. That's already incorporated into the fact that we cut down our supply by 200. And you can follow all the way along. If something is used on Tuesday, you can't use it again on Tuesday for cleaning. You have to clean it for Wednesday or clean it for Thursday, and the same thing if something is used on Wednesday. So now what about that's our cost matrix. So it's the cost of having a supply from one place, from one of these groups, meeting a demand in another group. What about these numbers? Where did these come from? Well, in a sense, we kind of did this these kind of numbers kind of come from building something that is balanced to start with. Now, there are other ways of formulating this problem. This is just one way of doing it. You could structure it a little bit differently with some artificial rows or columns and have it work out the same way in the end. But where did these numbers come from? Well, think about when we use them on Monday. If something is used Monday, our problem says we have 800 right away. So the 800 is the supply of things that are used on Monday, because we have to use 800 caps and gowns on Monday. Tuesday, we have to use 600 from the problem, so that's 600. Used on Wednesday, we know that 400 items are being used on Wednesday. Now, what about the rest of it? Where did this 1900 come from? It's put in there to balance things out. So purchasing new has to cover everything else. We know exactly how many were used on Monday, Tuesday, and Wednesday. There is only one more way that things can be purchased, or that we can get a supply. It has to be purchased new. So that number can be whatever you want in it, just so long as it satisfies it. But if you put 1900 in there, it balances it, which means that we are going to end up with a balanced problem, because there is absolutely no reason to buy any more than that, but you could end up buying that many purchased new. All right. And again, this problem can now be solved. You can see that we have the big M's in there. We have the 2's, so you can start by circling any of the 2's, working from there with the problem. Give this a try and solve it. Okay, that was a short lesson looking at some alternate uh, problems that can be formulated as a transportation problem. A big part of doing linear programming in reality is in structuring the problems. If you can recognize that you have a problem that can be solved in a certain way that has an efficient algorithm, that's the first challenge. Taking the problem and putting it into the proper form. Solving it after that is the technical one, but both parts of those are critical for actually applying linear programming in the real world.